Okay. Shh. I'll play my harmonica. I will. I will play my harmonica. Okay. All right. 3, 2, 1. Everybody, welcome to CS61C Lecture 3. Woo! I want to give a shout out to anybody online watching these webcasts. I got some email from Nishant Varma watching from India. I enjoy having your email. Anybody else watching online as a lurker, send me email, ddgarcia@csberkeley.edu, and let me know that you're watching, and I'll give you a shout out. Get your clickers ready, everybody else. Log into your web clicker, get them ready right now. There's a question, bam, right, coming after the slide. Go. In the technology in the news, shh, that's a silent process. In the technology in the news segment, I want to share always some really cool stuff that's happening. The first stretchable OLED was displayed and demonstrated by folks, researchers at UCLA, and that's awesome because that means that you could have wearable electronics that bend and happen to stretch with fabric. It could be incredible. So this is the first little research breakthrough that could yield a whole nother level of interaction, which would be incredible. So that's really cool stuff. Get your clickers ready. Good stuff. Okay. All right. So if I could borrow and have water in that, would be great. Just water? That'd be perfect. Okay. You guys all ready? You guys. No. Wait. What's happening? No what? Air Bear is slow. Air Bear is dead. Seriously? Dead? Seriously? Oh my gosh. All right. How about this? Keep trying. Maybe I'll ask the questions later. Okay. So I'll skip past that question. How about this? Going right to here. Oh, I wanted to show you this one. Bam. You can all, in theory, be in the class. Wait list, 17. Available seats, 17. Put the 17 equals to... Okay, so that means you have to now move around. You have to now adjust yourselves to wherever the open spots are, but make it happen. I want to welcome you all to the class. It's awesome. And eventually, there are actually still spare seats here. Now, these people in the aisles for fire code, you should all be in the seats. Raise your hand if you have a spare seat next to you. Raise your hand if you have a spare. See, look up. Go, folks, go sit in the chair. Go. Be active. Don't mind stepping over. And as you're sitting in these seats, go to the middle. Like, you guys should go move middle so that as you're going in, you leave a space at the edges. So it's late for people. Thank you so much. It's good people who are coming in late. All right. In review, we saw some binary representations. I've given you some n bits, and you say, it's like I jump, and I say, please jump, and you say, how high? I give you some bits. And you say, these bits are nice, but how am I supposed to encode them? What's the encoding that's behind it? What's the semantic piece of those bits? And I say, oh, that's an unsigned number. You say, oh, it's unsigned. It's obviously this number. Bam. No, it's one's complement. Oh, it's obviously bam, that kind of thing. So that's really cool. 5 different things we saw. The 2 that you need to really remember, maybe 3 that are used in many places. The 2 that are most popular are unsigned and two's complement. Unsigned corresponds to uint. In 64 in the C99 standard, and two's complement is ints, and that's the same as Java. Bias is also important. We like bias as well. The meta points are really critical. Ain't no free lunch, which is the bottom one, and also we make design decisions to make our hardware simple. We're going to see that over and over again. Bless you. All right, so 2 questions we'll skip until Airbus comes up. Has there been an update to ANSI? Today's lecture and Friday's lecture is Intro to C. The key meta point is you cannot just learn C from these 2 lectures. There's no way. You have to actually build it and do it. Your first project is in C. That's going to help a lot. Also, you have labs in C, homeworks in C. You're doing it. You're learning by doing. So don't say, well, I listened to both lectures, but I still have questions about C. Yeah, you're right. You're going to have a lot of questions about C. Use Piazza. Make sure you do Bright and Harvey reading. And make sure you look at the extra set of slides I'm going to give you as a reference. We used to have 3 lectures on C. You know this class is the old 61C, but squished to add this really big worldview of warehouse scale computing, multi-core stuff, which is really valuable and really important, and I bless that. But the reality is that means some things had to get squished. So one of the things you're seeing in front of you is a 3-lecture 61C Intro to C series becomes a 2-lecture one. So what I did last night, I spent a lot of time looking at the slides, and all the things that are usually confusing to students, I squished into one lecture. So I'm going to try to make Friday's lecture all about the questions that you normally can't just read a slide and understand. The extra stuff I'll just put to a slide and read. So you'll have a whole set of reading of 30 slides, which you'll go through, and just facts. They're not kind of big question stuff. The real thing that confuses people, like pointers and strings and arrays and how that all works, that's what I'll cover. The stuff that confuses people, I'll talk about. The stuff that's easy, nobody ever asks questions about, that'll be for free to read on top of that. So C99 was an addition to ANSI. The book that you have is nORC from the mid-'80s. C99 was a way to say, boy, there's a lot of things we certainly could learn about that, learn about how to make C better. And some of them are declarations and for loops like Java, Java-style comments, Java-style this, Java-style that. They learned a lot about success of Java. And one of the key things that I'm going to talk about here is the int types, where you have explicit integer types like explicit width to integers. In the olden days, ints were 16 bits. And then they became 32 bits, and now ints are 64 bits in some systems. So to make it clear how wide an int is and how much space you're using, you want to use int types, and that's part of that. And that'll say that's like the int underscore 64, like that. Okay? But you have to have a compile flag to make. Don't forget this compile flag, otherwise your C that you've been writing in C99 standard that will not be interpreted correctly. Okay? And again, this is my disclaimer that you can't get it from these lectures. I kind of said it. This is what it says. Here are some other places to go. K&R, you has to have. Java in a nutshell. If you are a Java fluent person, these are really cool. That's a really cool free article about how Java differs from C. And Brian Harvey has some great course notes, as well as the notes that I'm going to skip from Friday. So in general, how does C work? C differs from Scheme and from Java in how it takes source code and makes a running program. The way C works, it is a compile-run process. And compile really has some pieces inside of it. Scheme is an interpreted world. We'll talk about the differences and the values of that. So Scheme is an interpreted world. Java is compiled, then interpreted world. But C is just compiled, then you run that code explicitly. And that's what Java learned. Java said, what that produces is, you produces machine-specific code. When you compile, it's machine-specific. Java compiles to this kind of uniform language which you can interpret on all the architectures. But in C, one of the issues you'll see is you compile it for a specific architecture. That's why that's in blue, architecture specific. So that, for decades, was the kind of bugaboo. I'm going to write some C code, but yeah, I'm on a different architecture. Oh man, you mean I have to port it? And port it means understand how your architecture is different from my architecture. Is it little endian versus big endian? How big are your integers? What other libraries do you have that I don't have on my system? All those annoying things that make porting annoying, that make, I might be able to use a huge library that you don't even have, which means I have to rewrite the library myself. Ridiculous. So that's always been a bugaboo in the back, in the side of C. So, and this is the porting bullet I talked about here. In Scheme is interpret, I said that. And in C, there's kind of 3 stages. We just say compile. You call GCC and out comes a running program. That's because GCC is doing many things at once. It's compiling, it's linking, and it's assembling. Those are the 3 things it's doing. Then it actually loads it when it actually runs it. We'll learn about all those things. CALL, compiling, assembling, linking, loading. We'll see about that in more detail later. The advantages of compiling over an interpreted language, like Scheme, or like interpreted C. You could actually interpret C. There's no reason why C has to be compiled. You could try to interpret C. In fact, there was a company for a while that we actually paid money to allow you to have a C interpreter where you could be there and be typing valid C expressions. I think there's also a Java interpreter you can get with Eclipse. Is that right? Called Guild. Anybody know about this? No. All right. It was old school. It was cool. You can be living an interpreter, just like the Scheme interpreter, the read, eval, print loop, the REPL, typing in valid C or valid Java. And so you could do that as well. But in general, the advantages of compilation are great performance. That's why C, you can't touch it. C produces code that's run explicitly on the hardware. There's no fluffy where there's an interpreter between there as it is in Java. In fact, that was Java's problem early on, is that Java's interpreter, when it was actually running Java code, was 10 times slower than C. I mean, really slow. And they've now done a lot of work to make that much better. So the Java performance issues aren't there anymore. But it was there in the early days of Java. Compile time is kind of one of the big deals. You have to pay the piper at some point. So you either pay the piper at the interpretation runtime or you pay him in the compile time. So C, you pay it up front, huge compile time in terms of there, and then running is instantaneous. Bam, it's fast. It's as fast as it could ever be. Blink, blink. The disadvantages, I mentioned before, you compile down to some architecture-specific system. Java has this really cool thing where they compile to this architecture-independent system, the Java bytecode, and you learn from there. But normally in C, in most languages, we say, I'm going to compile it. Oh, OK. That means you're going to compile to some architecture-specific thing, which means, and you probably are all Intel-based, so you didn't know. But there are other architectures out there you may not know about. There was PowerPC. There's Intel. There was Spark. There's Alpha. Give me some more architectures that I'm forgetting. There's ARM, there's AMD is Intel compliant, but other architectures? The Atom, yeah, actually there's quite a few different ARM flavors, that's true. There's the Z100s, there's, I said PowerPC. There's quite a few, so all of those, if you have a different machine, different architecture, you can't work. And even though PCs and Macs are the same architecture, there's OS libraries that make interoperation, unfortunate. So even if you have the same Intel hardware, you still can't just run a C stuff on the Mac on the PC because other libraries come in and factor into this. So again, rebuilding, porting, I talked about that. And this is the slow piece of it. Make a change, compile it, and run, that's annoying and kind of a bummer. Somehow this battery's low. To get started, you have a main. So that's very clear. You have two arguments to main, int argc, char star argv, bracket, bracket. And what that means is, very simply, argc is an integer. You might ask why it's not an unsigned integer. It's because I never have negative arguments. But it's an integer telling you how many arguments you have. And it includes the executable itself. So that means if I say sort, which is the name of my executable, and my file, argc is 2, argv sub 0 is the string sort, argv sub 1, or not sub 1, argv of 1, the array notation, argv of 1 is the string my file. Does that make sense? It's useful, by the way, that's extremely useful, because if you are in the code, you might not know what your program is named, right? Your user, at the Unix level at least here, looking at a Unix command, could rename sort to be my sort. mv, which is a Unix command for changing the name of something, sort to my sort. And so the worst case I've seen is people say, error, and it'll say, but the program name is my sort, right? And it says usage. There's always a usage string, and it'll say usage, sort. But even though the executable is named my sort, because the person has hard-coded the name, now made a copy of the name in their code, what they should have said is, error, argv of 0. Argv of 0, which is the name of the program, is how you call it. Get it? Argv of 1, like my sort, error, 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 here's how you'd call it. You don't actually write the word sort in your code. You write argv of 0 in your format string. Okay? Questions about that? This is all easy stuff. The way you declare variables, it gets harder at the point of stuff. So when it goes easy, I'll just go a little faster. Let me move this over here. This is annoying. By the way, let me know how everybody's is going, because I do want to check back in with that question. Variable declarations are very similar, except that they have to be at the beginning in old school C, but you have new school C. You're using C99. So you don't have those constraints anymore. They can go anywhere. So we love that part. That's one of the things we've learned from Java. Don't do that. So this is only incorrect in the old school C, but it's correct there. I'm going to say this about 10 times, because students always make the mistake. A variable may be initialized in its declaration. If not, it holds garbage. So that's something they fixed in Java, where when you declare a variable without initializing, there's a default value for that, usually 0 or null or something like that. We don't have that. If you make a pointer or a reference, it holds garbage. You can't assume that. You always have to set it first before you can use it. There's no assumption of 0. That's a big difference. That's a really big difference and a source of a ton of problems. Okay? So what's in a variable before you declare, after you declare but don't initialize it? Garbage. We're going to say this over and over. Okay? So this is the first time you actually may have seen this. This is the beauty of 61C. I am lifting the hood on how the machine works. For the first time, you have to understand what addresses are. You probably have been able to survive up to now without actually knowing about an actual number in the machine, which is where your stuff is stored. You might have said, well, reference is there. I don't care where it is. We're going to care a lot where stuff lives in this course. And you're going to know about that. So it's kind of cool I got to teach you that. We consider memory as a huge array. Okay? How big is your array? They often ask. Well, it is as big as your address space. We learned in discussion this week that n bits of address space can access 2 to the n things. So if I have 32 bits and I am byte addressed, How many different bytes can I have? What's 2 to the 32? You remember that equation? Remember the 2xy? Did they do that, guy? Remember the 2xy that you're supposed to memorize that you didn't? No. All right. So go do that for homework, okay? 2 to the 32 is 4. How many? Mega, kilo, giga, giga, right? The 3 says you go to the third one. The first one's kilo, the second one's mega, the third one's giga, okay? You got to memorize that. So 4 gigabytes, so you have 4 gig. 4 gigabytes of RAM. So that's how big my address space is. It's one big 4 gigabytes of RAM system. Now you're going to say, but Dan, I don't have 4 gigabytes of RAM. I peeked inside my thing, I don't have 4 gigs. I happen to have 8 gigs on this guy. But I don't have 4 gigs on most laptops or small systems or things we used to use 10 years ago. What do you mean? Don't worry about it. It's a beautiful abstraction for now. You have 4 gigs. You're like, but I don't have it. Yes, you do. It's really cool. All right? You're going to thank me later. This abstraction, you're going to thank me later, okay? And I'll tell you why you don't and how we can make that beautiful abstraction work for all of you users. So each cell stores some value. Each byte in there stores some value. Sometimes the values are 4 bytes wide. That's called a word. I remember there's a question on Piazza what a word is. In this world, a word is always 4 bytes wide. Words are usually the size of things. It depends on the architecture. Sometimes words are 8. Here, words are 4 bytes wide. They obviously use unsigned numbers because we don't have negative addresses. That doesn't make any sense. Don't confuse the address referring to memory location with the value stored in that location. So here is my big array. I'm going to throw it on its side because it prints a little easier. And here is the addresses. It's like house number. This is the house address. Red is the house address. House number 101, house 102, house 103, house 104, and I'm storing 23. Here's a little aside. If I have house 104 and 23 there, how big can that number be? 23. Could that number 23 be 2 trillion? This is interesting. Remember, when I say this is byte address, these are different byte locations. A byte means I have 8 bits. So what's the maximum range of an 8-bit number? Because this is byte addressed, and I have 8 bits in that byte. Well, if it's unsigned, it's 255, and if it's signed, it's 127. Right. Good. So that is the biggest number. So when editing my slides, good thing I didn't put a number bigger than those 2 numbers when I was putting the slide. 23 certainly fits in both of those guys. Okay? A pointer. So now I'm going to go slowly because this is the part where people get confused. A pointer. So any questions, by the way, on the first hard part? This is kind of hard part, step 1. We okay between addresses and values? Blue guys inside the boxes are the values. The address, which is like the label on top of it where it lives, is the address. Okay so far? All right. Yes? Okay. Yeah, question, go. How does the system know? Great question. How does the system know what it is? And the answer is, it doesn't. It just has bits there. And you're going to know how they are by how you treat them. What kind of assembler instructions you use to it. If I do a logical operation, then I'm going to say, well, I guess that must have been a logical 32 independent bits. If it's going to be an assigned addition, I guess it must have been a signed number. It's kind of cool. Floating point multiply must have been a floating point number. It's kind of cool. And the cool thing about 61C is you realize that I can do something. This is what's so cool. Here's 32 bits. I can interpret them any way. So it was a floating point number, and I want to make it negative. So I can either call, floating point, f equals negative f. Or I know that those 32 bits are interpreted the following way, in the way the floating point numbers are stored. The leftmost bit is the sign, because it's a sign magnitude guy. And I can go in and mask that out and remember what it was and flip it and store it back in there as a logical operation, like as just independent bits, and I've made the number negative. I could poke at the bits and change the number rather than, it's really cool. So it's totally freeing that you can treat them as 4 characters and print them out. Like, what? It's a floating point number. No, they're 4 characters to me. It's really very cool. So we'll see that a little later. So next hard big thing, a pointer. Okay? So a pointer is the name for a variable that holds an address in its value. Oh my gosh, too much. Okay, let's start again. It's a variable. It's a box, like a box, right? The houses have boxes. They have the house numbers on top, and there's a box. A pointer is a box where inside the box, it's an address. Is this 104 a pointer? This box a pointer? It could be. That could actually be pointing to slot 23. Is this a pointer? Well, here's a piece of it, which is pointers are 4 bytes long. So it really is not 23. It would be kind of like 101, 102, 103, 104 together. Is that a pointer? Because pointers aren't just a byte. Pointers are bigger things. Okay? Pointers are 4 bytes wide. We'll see that. Okay? All right. Partially, why is that? Because I have 32 bits address space. So because I have 32-bit address space, that's how wide my pointers must be. Does that make sense? If I have a 64-bit address space, if I have a new 64-bit Mac, then my pointers are, by definition, 64 bits wide, because that's how you'd address your full memory. So the pointer width is the same as your address space width. Okay? Okay, so let's play with this now. Okay, here's my 23 location, and here's pointer P. Now, again, this is a little bit smoochy because I told you about the size of words, and this Peter's only is holding a byte, but work with me for now, okay? I haven't told you the system in this particular picture is a 4-byte wide system. So maybe this is a, maybe I only have 255, 256 memory locations, in which case a pointer could be a byte. This pointer points to X. The pointer holds the address of where X is in its value, meaning in the box for P, that 104, which is the address of somebody else, is my value. And then I know P is a pointer. Okay? Question in the back. Yes?
So the value is like 5,000. Where is 5,000?
This is where the analogy breaks down. See, that's where I kind of confused you about this system being 4 bytes wide and the whole thing. In this particular picture, I'm drawing a picture with a special new system on my key. This is a computer running my key, which only has 256 pieces of memory, and it's byte addressed, and I only have 8-bit wide address space, not a 32-byte address space. Then this is valid. So I'm sorry for confusing you about that. Okay? So far, but this is still correct. The pointer holds 104. Y could be a pointer, and X could be a pointer. In fact, everybody can be a pointer if you think about them. Because everybody's value max wide is 8 bits wide. The address space is 8 bits. It actually would work on this system. It's kind of cool. Everybody could be a pointer here. So let's do some code. Here's C now. How do you create a pointer? In C, you say int star, or whatever you're pointing to, you have to have a star in front of this. So let's read this. Int x, means make an x, which is going to be an integer. Int star p says make a box. The system now knows that p is going to be a pointer to an integer. I'll say it again. By saying int star p, it says p is a pointer to an integer. The variable p doesn't mean anything. Could be x, but we usually kind of use p's and q's for pointers just to kind of make it easier. But there's nothing special about p semantically, right? You can call pointers anything. All right, but notice, question mark is my rendering of garbage. It's very important, okay? The question mark is garbage. So what is p point to? Class? No, not to point to garbage. You say, I don't know. It doesn't point to it holds garbage. Where it points, it's like they just had Irene. And Irene, my mom's house, a tree came down, and what did it? It knocked out a power line. And the power line was live. So it was like this little wire going, zzz, zzz. You know, seen those like horror movies? Zzz, zzz, don't get near it, zzz, zzz, like Final Destination or something. Zzz, zzz, don't grab it, don't grab it. Oh, wait, what do you mean? And it dies, right? So it's like, zzz, zzz, zzz. It's like this crazy live wire, right? That is what P is. P is, I don't know where it points. It could change. Who knows, right? The value is garbage. It points who knows where. It could even point to itself. All right, so x also garbage. Who knows what the value of x is, okay? Now, x equals 3. Now I can finally use x because I've assigned x, so now I can use x somehow. Next line, p equals address of x. Now, let's try I read this. I didn't read p equals ampersand x. I read p equals address of x. When you see that code, that's how I want you to read it. P equals address of x. And what that does is set p to point to x. Now I ask you, what is the address of x? 100, 200? You say, I don't care, Dan. No, really. It's important that you say, I don't care. All I care is that there's a red arrow that starts at p and ends up at x. I actually don't care where x happens to live. All I need to care about that this connection is made between P and X. Does that make sense? So I don't care where X actually is. If you're hacking your system, you want to see where does X actually live, I can show you how to do that. But at this point, you don't care where X actually lives. Yes, question? Great question. Class, what do you think? If the value of X changes, does P's arrow change? No, P's attached to X, and I can get to X through P. That's the value. I can get to X through P, but if X changes, P still got him. I got you here. Okay? Yes. My hand's in your pocket. The amount of money in your pocket can change. My hand still stays in your pocket, right? I like that idea. Let's try that. Especially with the wallet pocket. If we can do that. Yeah, go ahead. I lost you. If you have a Y, make it 4, then what happens?
Then could you say Y equals the address of X?
If Y is not a pointer, you can't do that. And so the question was, if you have a value Y, can you say Y equals address of X, and Y was a normal integer? That's the point of the compiler. That's the point of this typing system with the stars. It'll kind of give you early warnings. C is going to let you basically have the longest rope in the world and hang yourself about 9 times through Sunday to do that. But one way that it helps you is it helps you with this pointer stuff. It'll give you a compile error saying, you're assigning an integer to a pointer. That's not so cool. So C is really loose with its typing, but it is a little strict with its pointer stuff, at least in the point of errors and warnings. Yes, question?
If you call printf on P and tell it to interpret P as an integer, will it actually put P as that?
That's a very good question. If you call printf on P and tell it to print P as an integer, what will it do? Let's save that till the end, because I think I have a peer instruction question that has that exact thing. So let's make sure your question gets answered by the end of the class, but I don't give the answer because I might give the answer to my peer instruction question. Yes?
If you initialize X again, does the address change?
Great question before. Similar question before. If I change X or initialize it again, I can't initialize it again. You can do it. You initialize it once. You declare it once. It'll say you can't initialize it twice. I can change it, but I can't initialize it twice. Yes?
Could you store a number in P after declaring it as a pointer?
If I change P, if I say like P equals 4, it's going to change where P points to. P now points to whatever lives at X location 4. That's how you would change P. Right? The P equals basically says, look, wherever X lives, like 102, I put P's value 102. And for now, I draw this red eye, which is semantically how I think of it, but P still holds the box 102. You should be able to draw that for yourself, and then just follow code. There's nothing magical here. All it's doing is go to the system, find out where X lives, and stuff 102 into P. This is a normal assignment statement. It just happens to draw a red picture semantically. Yes? It's interesting. So what if you point to like a big thing, like a structure or something like this? It points to the beginning of it. And that's useful when you want to do pointer arithmetic. We'll see that later. So it does that. Boy, a lot of questions come up on simple code. It gets harder after this, so we better hold up at some point. Yes, question? If you had another pointer Q, well, is Q an integer? No, Q is a pointer. That's going to give you a type problem, because you can't point to another pointer. You can only point to integers. That's what the type is about. You could get the address pointer, but you have to declare P differently. If you want to declare P as a pointer to a pointer, then you just say P is a star star, which means it's a pointer to a pointer. We'll see that in a second. We'll see that actually on Wednesday. Yes, question? These are good questions. Can I change where X lives in memory? No. It gets a little complicated if X isn't a local variable like this. If X kind of is Friday, I'll answer that one, because you could reassign X to be some other place, and it's a little bit more complicated next. Okay. So how do you get the value? You haven't even get to halfway of this slide. The value pointed to star is the dereferencing operator. Like, Star says, follow the pointer. So watch this. P points to %D is a normal signed integer, and star P. Star P is exactly the same as X. Wherever you see the word X, you can write star P. Okay? It says, go to P, which is the pointer. Star says, follow it, and it happens to be X. So now, in your mind, replace all star P's with X. So P points to this. It would print out 3, obviously. Okay? P points to 3. So far? Good. Yes, question in the back. You gotta wave your, if you wave all the way in the back, it's really high up from my neck, so you gotta wave your hand. So yes. Star p equals 3. That's exactly how you would change, how you try to change. I mean, here it's 3 to 3, but if you said star p equals 5, you'd change x's value. That's exactly right. So remember, star p is x. What did I say? I mean, like, the answer should be, what did I say a second ago? Star p is x. So where you see star p equals 5, that's the same as x equals 5, therefore x would change. Right? Yeah, go ahead. Louder. Correct. You cannot have p equals x because x is an integer, p is an integer pointer. They can't be equal like that. You have to say pointer equals pointer or integer equals integer. You can't mix the types like that. That's exactly why the compiler would warn you. Yes, question. Last one before we go on. You can't put ampersand of x on the left-hand side. Only variables by themselves on the left side of an equal sign. Okay? All right. So this is important to kind of a meta note. The star is used 2 different ways. The star above the star up here is used to a declaration to say, in the future, p is a pointer to an integer. This actually says, do some work, right? So the star in the declaration is different than the star actually in the body, which says, go follow p and find out where it's pointing to. Okay? So here's a fun one. Ready? And you guys have already asked half these questions, so I can go a little faster. How do you change a variable pointed to? Remember, this is p pointing to x like before. Star p equals 5. What did Dan say? Star p is like x. So what's the result of this guy? X changes to 5. But p doesn't change, right? I change the amount of money in my pocket, but my hand is still in your pocket, but I'm standing still in your pocket, okay? All right. So I'm sorry that this is like a reveal thing. It's always annoying. Okay, here we go. So now, people always say, oh, pass by reference. No, almost every language you're going to play with is pass by value. And a value means it's the copy. It's not the reference, it's the copy. Oh, but it's a point of reference. No, it is the copy of whatever it was is being passed as the argument. Okay? So, here's something called add1, in which I want to change the variable outside of me. So, int x, I'm in main, and I have a y, which is 3, and I want to increment y. So I'm going to call add1. Let's try it. So I'd say add1 of y, and I hope that y is now 4. That's my intention with this code, possibly buggy. Here we go. Y is still 3. Y is y. ¿Por qué is y still 3? Weishima, y is still 3, folks. All right. There we go. Okay. Well, what do you think? Because now it's passed by value. Nothing about y was sent into add1. Nothing other than its value. So add1 gets literally 3. How is it supposed to know how to go back to y? Y has an address of 102. Let's make it 100 so it's a multiple of 4. It's 100. Y lives at 100. What's happening here is there's a local variable that lives on for just one line, x. It wakes up. It gets the copy. It gets the value passed in, which is the 3. X locally, it's like scheme, right? X is now bound to 3 in that little world, in that little scope, okay? X equals x plus 1. So the line right below that, x is now 4. Y is sitting over here at 3 going, I don't know what you're doing over there. I'm sitting at 3. You're not going to touch me. Unless you get 100 anywhere, unless I give you my 100, tell you where I am, you don't know how to change me. That's why it's critical that it's passed by value. Okay, questions on that? So now, you've seen some pointer stuff. Now you know where I'm going. If this doesn't work, you see where okay, so now, here's how we fix it. How to get a function to change a value. That's the whole thing. That's what you're trying to build. Oh. Before this lecture, that looked like Greek to you. Like, what is these stars? I mean, what's that? But now it makes sense. What's this doing? You're passing in a pointer. You're changing the thing the pointer points to by 1, and you're done. This has a side effect. We have now left the world of functional programming, right? Because this has a side effect. There's no return value. Look, this is a void, right? You know what? Whenever you see void, you think side effect language, right? So, y is 3. Now, how would I call it? Here we go. Am I calling add1 of y? No. Good. Because I'd pass the 3. It doesn't make any sense. I would pass in add1. No, you're not saying ampersand. I told you not to say that. I caught you. address of y. See, that makes sense to say that word? Now you know what you're saying. What does ampersand mean? I don't know. It means address of. So say address of. Add 1, address of y. What's it passed in? What's the value? What's the copy being passed into add 1 now? 100. It's where y lives. Now, it's where y lives. Now, p, local copy, also has 100. Somewhere over here, y lives at 100, has the value 3. X, some local variable, lives, I don't care where it lives, but it has the value 100. What does that mean? Red arrow pointing from my local p back outside of that subroutine, back to the original y. Get it? So that pointer goes outside of the scope of my guy, points out there. Star p equals star p plus 1. Really, that's the same as saying, remember now, just like before, when I see star p, I can say y now. So it's like saying y equals y plus 1 in the scope of the outside guy, right? I'm following the star p. What does it point to? Oh, it's 3. So 3 plus 1 is 4. Star p equals that, which means, I think I said earlier, only you can have variables on the left. You can have variables or star variables, obviously, on the left, because I'm changing that, right? So star p equals star p plus 1 means that y is now 4. Let's pause, reflect, make sure we get this all part. 100 is being passed in. Local p gets the value 100. When you say star p, it says, oh, go to 100. That's over here now. Okay, get the value. Oh, it's 3. Pass it over here to the guy plus 1. It's now 4. Okay, and now go change whatever that was pointing to be that 4. Okay, walk back over here, and 4. It actually clobbers it. So whatever the value was before, it's being overwritten. Okay? Being incremented. Okay? This is still pretty easy. It gets much harder on Friday. Friday's going to be a lot harder. So this is still baby steps. We're going to start running on Friday. Question in the back. Yes?
Does calling a value of a pointer take longer time than actually calling that?
No. The question was, does somehow requesting the value of pointers take more time? It's all one. They're all free. We'll see. When we go to MIPS, it'll kind of, how much time stuff takes, it's so cool. This fuzzy world of how much time stuff takes will just be literally revealed. I will open up the hood again. There's like a hood. It's like Alien with the inner mouse. There's like an inner hood that I'm going to reveal like that, and it's going to be amazing. You're going to say like, oh my gosh, I see it. I get it how long things should take and why logical operations are longer than multiplies, all that stuff. It'll be really clear. Awesome. Okay? So, why do we have pointers? Okay? They can point to anything. Any data structure you have, integer, any built-in type, or a struct, which is the way you make your own data types, a pointer can point to them. Okay? However, pointers normally only point to one type, and that's for your compiler. That's how the compiler can help you. You know, you're pointing to a structure, but then you're assigning it you're saying that pointer equals another pointer, but he's pointing to an int. That's not the same thing, and he's going to warn you and say, don't do that. Okay? I don't know why that becomes a masculine thing, because he angers me so much. That's stupid compiler. So that's the thing. So there's that. So there is something called a void star. A void star is a way to make a generic pointer. It's kind of something we shy away from for new programmers. You use it when you know what you're doing. So don't go there until you have to, when you know, because otherwise the compiler can't help you, right? The void star says, I know what I'm doing, trust me. It's a generic pointer. I can point to here and point to there, point to there, point to there. The compiler then can't help you to make sure you're not assigning two things that are different together, okay? Because you're always doing void stars. So don't use those. Bad things happen. Paired structure question. Actually, how are we doing for the clicker things? Are we okay? Maybe and the air bears and stuff, air bears is okay? Hopefully, I give you enough time to all get in and do web clicker stuff. I can even use mine to see how fast mine goes. Okay, here we go. Question is, how many syntax plus... Now, this, by the way, shh. This is a silent test on your own. Don't talk until I tell you to. And take your time. I won't put a timer on this. Think about this. Look at syntax or logic errors in this code. The goal is to say, I got a pointer and an X and a Y. And remember, it's C99. Don't forget that. Okay? Y equals this weird thing. Okay, and then int z, and then flip sign, which is supposed to negate it, right? Because look at flip side, star n equals minus star n, got that? And then printf what those guys are, okay? So wherever p is pointing to gets flipped, hopefully, and then I print out what x, y, and p are. Does that make sense? So y gets a value, x gets a value, z is actually not used. But it's okay because z is after an expression, and so I'm testing that part too. And then p is this pointer that gets set in there, maybe or maybe not. Okay? So click away. I got 36 people. I'm going to try to click myself now. And don't talk, because this is really the silent part. Then we'll have a discussion. We have 10 minutes, and we're good on this, okay? So do that. I'm going to click over here. Web clicker. Does it remember me? No internet connection. That is some annoying stuff. That's really annoying. I got to join Airbros now? Ugh. This is like Brian looking for signal. People trying to click with a signal. I'll click if I get it. I can just get it to click. All right. By the way, I really, really, really had hoped that we'd be in the 300s of clicker people today, because the question I'm going to ask you, I want to have the whole class tell me what the value is, and having only 150 people or so is like half the data. This is good. I like 170. I like 200 more. And I like 300 more than that. Come on, 200. Come on. Yes. Yes, thank you. Come on, 250. Don't talk yet. I want to make sure you guys all vote, in isolation. Any trouble, by the way, with the web clicker stuff? Are we okay? Is it okay? Is it giving you the thumbs up on that one? Okay, good. Thank you. I'm getting some thumbs up. Excellent. Okay. Are we stabilizing? 230? 230 is pretty good. Okay. So now, we have 8 minutes. Talk to your neighbors. I do want to have 2 more clicker questions after that. How many syntax errors? Okay, let's come back. Let's vote again. Come on back. Register your preferences. Your web clicker should be asking you for the second thing, I think. Cool. I'm watching the web clicker interface. That's kind of cool. Awesome. Is that working?
Yeah.
Oh, that's great. And you voted? Okay, great. 117. Come on, folks. Vote in. Any announcements? Let's go. 2:06. Come on. We got to get 2:30. Quick. 2:30. Come on back in. 5 minutes. 3, 2, 1. And hold your. I'm still growing and stopping. Okay. 2:15. So let's see. How about this, huh? I really want to see how you guys did. This is always fun. It takes a while to kind of bring everything in, coalesce all the stuff in from the web, I think, is how it's happening. Yeah, web clicking does slow it down in terms of the wait process. Displayed, is that, my whole thing is dead. How about I just show you the next slide? I think I hit it. The answer, 5. And here's the 5 that I get. Remember, I said logic plus syntax. C is not main is not a void, it's an int. You return values from main to the shell, which tells you if you have success or not. This semicolon shouldn't be there. Obviously, that's not so cool. There's a semicolon missing here. This flip sign, I love catching students. I hope I caught you, because by you going, oh, now you won't make that error in your own code. You can't use a negative sign. You can't try to attach words together. You have to use camel case, which is up and down capitalization, or underscore. But a minus sign, a dash, does not work to have names of things. That's really important. Shh. And this star P, I'm printing a %D. %D means printed as a signed integer. If I have this is P, I probably needed to be star P. The previous slide was P, I believe. If I go back here, the previous slide was P. It has to be, I probably meant star P, right? X, Y, and star P. I don't care where it is. I want to care what it's pointing to. And so it should have been star P if I have %D here. They didn't match. That was a logical error. Okay? Stay with me. I want to now ask the question that I didn't get to. I have 2 minutes. Let's everybody vote as fast as possible. Ready? Here we go. Get your slides out. Ready? Go. Before the class, I, student, would say that I am a solid C programmer. Strongly disagree, because I've never coded and I don't in C, and I don't know Java or C++. Mildly, I've never coded in C, but I do know Java and or C++. Neutral, I have a little bit of C. I've done a fair bit in C, and I've coded a lot in C. Ready? Go. I'll give you 30 seconds. This is a fast one. There we go. It's going fast. Fast. 200 in less than 30 seconds. Not working. Web clickery things? Not, okay, yeah. These things are slow. I'm sorry about the speed of the world. Okay, 203. Okay, here we go. Come on, 230. How long? Come on. Fast, 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 fast. Okay. And stop. Come on, don't take an hour. Please don't take an hour. Don't take an hour. I can't take it. It's still gathering from the web. And I can tell while I'm waiting. The numbers are 5 in the first one. Most of you know Java but not, or something else. And then some of you have done this. So the E is going to be the rock stars who are just blown through the section. The A folks shouldn't be here because that's a prerequisite. That was the kind of a thing. And I do have your names. So sorry about that, but you're now busted. You're now officially sitting in the course because you really shouldn't be here. Ready? And next one. How about Java? This is specifically actually about Java. And this is relevant because we're going to have a project in Java. I should probably click Start, right? That would be helpful. Project in Java, and that's really important to know who the Java experts are, who's never done. Oh, what happened? No. They're about Java, and it says, how much of a Java programmer are you? I disagree, I don't know Java, and I don't even know C or C++. Or, I don't know Java, but I do know C or C++. Then I know a little Java, I know a fair bit, I know a lot of Java. Okay? Go fast, go fast, go fast, go fast. By the way, it's okay not to know Java for this class. Yes? That was supposed to be C. That's okay. If you were the A, but you said Objective C, then you're okay. From the last one. Okay, ready? Stop. This is unbelievable. I've never seen this. By the way, it was okay not to know Java, so you don't have to lie for this one. You maybe better to lie the first one, but I got you. But this one, I got 0, 5, 13, 50, 32. So basically, people know Java. However, 5 of you have never coded in Java, which is okay, but it's important for us to know when we do the MapReduce project, we're going to ask that anybody who doesn't know Java partner with someone who's on the D or E here. Does that make sense? So at very least, you don't having somebody, that's why it's a partnership thing. So we've got to cover, we're going to have a Java project. Java isn't required for this course, but only 5 of you have never done Java at all between A and B. So you guys will partner up and learn some fast Java, okay? See you guys on Friday. Thanks, guys.